Today, as we continue our study of sets, let's talk about complements, subsets, and Venn diagrams. I want to begin by talking about something called the universal set and its complement. The set of all elements that are being considered is called the universal set. We'll use the letter capital U to denote the universal set. For example, if we were doing a survey on the month in which a person was born, then the universal set would be the set containing all 12 months: January, February, March, April, May, June, July, August, September, October, November, December. There are no more months to consider. That would be our universal set from which a particular month would be chosen for a particular person. The complement of a set A, denoted by A with an accent symbol as a superscript, is the set of all elements of the universal set U that are not elements of A. So you can't define the complement of a set until you know what the universal set is. For example, if the set J is a set containing January, June, and July, then the complement of J would be you go up to the universal set and you cross out the elements of J, which would be January, June, and July. That happen to be the months that start with the letter J. And what you're left with is the complement of J. So the set containing J complement is a set containing February, March, April, May, August, September, October, November, December. Let's try this example. Suppose the universal set that we're interested in is the set containing the counting numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. The set S is the set containing the elements 2, 4, 6, and 7. And the set T is written in set builder notation. It's a set of all x such that x is less than 10 and x is an element of the odd counting numbers. Two things we want to find here. Part A, we want to find S complement. So let's look at S complement first. In order to find the complement of a set, you have to know the universal set. So when we're looking at the complement for the set S, we have to go back up to the universal set and cross out any elements that are in S. And whatever's left is in the complement. So the elements that didn't get crossed out are 1, 3, 5, 8, 9, and 10. So S complement is the set containing the elements 1, 3, 5, 8, 9, and 10. Now let's move to T complement. First of all, I noticed that T was written in set builder notation. So the first thing I would do is write out T explicitly before even thinking about forming the complement. So we need to know what those elements are explicitly. So we're looking for the numbers less than 10 that are inside the universal set. That would be the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. But we also want those to be counting numbers that are odd. In other words, the numbers that are less than 10 and odd. If you look at the numbers that I have put in the rectangle indicating that they are less than 10, the odd ones are 1, 3, 5, 7, and 9. So written out explicitly, T is simply the set containing the elements 1, 3, 5, 7, and 9. Now you've done all this work, but we only found T. We want to find T complement, so don't forget, you've only found T now. We wrote out T explicitly. T complement is found by going back to the universal set and crossing out every element of T. If you do that, you cross out 1, 3, 5, 7, and 9. You're left with 2, 4, 6, 8, and 10. So T complement is the set containing the elements 2, 4, 6, 8, and 10. Just need to practice. There are two fundamental results concerning the universal set and the empty set. First of all, because the universal set contains all elements under consideration, the complement of the universal set then has to be the empty set. The complement of everything would be nothing. Secondly, the complement of the empty set is a universal set because the empty set has no elements and the universal set contains all the elements. So the complement of nothing is everything. The complement of everything is nothing. The complement of nothing is everything. If we want to do this symbolically, I could write U complement is equal to the empty set. And remember, there are two common symbols for empty set: the circle with the slash through it and the braces with nothing in it. So if I'm looking back at that first result, the complement of the universal set is U complement. It's equal to the empty set. Now, you don't have to write both of those symbols. I'm just writing them both for completeness because you see them both occasionally. You need to know that if you see either one, it means the empty set. The complement of the universal set is the empty set. That's the symbolic way of writing it. And the complement of the empty set, whichever way you write it, either the open circle with a slash through it or the braces with nothing in it, the complement of the empty set is the universal set. And remember that I don't have to write both of those symbols for the empty set. I just write one or the other. I'm writing both for completeness here. Let's talk a little bit about the concept of subsets. Consider the set of letters in the alphabet and the set of vowels, the set containing A, E, I, O, and U. Every element of the set of vowels is an element of the set of letters in the alphabet. Having said that, the set of vowels is called a subset of the set of letters of the alphabet. We'll often find it useful to examine subsets of a given set, so this is an important concept. Formally, a set A is a subset of set B, denoted by, and you see the symbol, it's the set A, and then the symbol is a sort of a sideways U opening to the right with a bar under it. A is a subset of B, if and only if every element of A is also an element of B. Just like I was talking about, the set of vowels is a subset of the set of letters of the alphabet because every vowel is also a letter. Here are two fundamental subset relationships that I want to emphasize. A is a subset of A. In other words, a set is a subset of itself by definition. And the empty set is a subset of A, and this is true for any set A. A set is a subset of itself, and the empty set is a subset of every set. So every set automatically has a subset equal to itself and the empty set. As we've done with other symbols in this course and in previous courses, if you put a slash through a symbol, it typically means not. A is not a subset of B, and look at the symbol. It's the subset symbol with a slash through it. It means that A is not a subset of B. To show that A is not a subset of B, we must find an element of A that's not an element of B. So if you want to show something is not a subset of something else, you have to find an element in that set that's not in the set that you're claiming it's not a subset of. Let's look at this and do some true-false. If I ask you, is this true or false? A set containing 5, 10, 15, and 20 is a subset of the set containing 0, 5, 10, 15, 20, 25, 30. All you have to do is start on the left and element by element look for that same element on the right. So you notice that the 5 inside the left set is in the right set, 10 from the left set is in the right set, 15 from the left set is in the right set, and 20 from the left set is in the right set. That's what you need to show that something's a subset of another set. So that statement is definitely true. How about this? W is a subset of N. Remember, W, the capital W, is the symbol for whole numbers. The whole numbers are the counting numbers with 0 thrown in. So it's the set containing 0, 1, 2, 3, 4, on in that pattern. The natural numbers is the letter N. The natural numbers are the counting numbers. They start with 1. 1, 2, 3, 4, ... which means it continues in that pattern. So you have to look at each element on the left and see if you can find a match on the right. And the very first thing you look at, which is a 0 on the left, does not have a match on the right. That means the statement is false. The whole numbers are not a subset of the natural numbers. How about this? the set containing 2, 4, 6 is a subset of the set containing 2, 4, 6. Now remember, we just talked about this. Every set is a subset of itself. And if you see, by doing the same thing we did for the others, there's a 2 on the left, it appears on the right. There's a 4 on the left, it appears on the right. There's a 6 on the left, it appears on the right. Therefore, it is true. But anytime you see a set compared to itself, a set is always, by definition, a subset of itself. How about this? The empty set is a subset of the set containing 1, 2, and 3. Now, if you remember what I said just a few minutes ago, you'll have this immediately, and that was the empty set is a subset of every set. So it doesn't really matter what's on the right. If you've got the empty set with the subset symbol, whatever you put on the right, it's going to be a true statement because the empty set is a subset of every set. That statement, therefore, is true. The English logician John Venn, who lived from 1834 to 1923, developed diagrams which we now call Venn diagrams that can be used to illustrate sets and relationships between sets, and I find them extremely useful, and I think you will too. In a Venn diagram, the universal set is represented by a rectangular region, and the subsets of the universal set are represented by oval or circular regions inside of the rectangle. This Venn diagram in particular shows a universal set U and one of its subsets A. The region outside of the circle but inside of the rectangle is the complement of the set A. So A is the set represented by the circle itself. A complement is represented by the area outside of the circle. We talked about subsets. Now I want to talk about something called proper subsets. A set A is a proper subset of a set B if every element of A is an element of B, and additionally A and B are not equal to each other. It's the same symbol as for subset without the bar. Think about this in a minute. The definition of a proper subset is exactly the same as the definition of a subset, except that it doesn't allow the sets to be equal. With subsets, we said a set is always a subset of itself. With a proper subset, a set is never a subset of itself. In fact, the only difference between the definitions of a subset and a proper subset revolves around whether or not the entire set is included or not. If the entire set is included, you can call it a subset. You can't call it a proper subset, though. Now remember, for a subset, we already know that every set is a subset of itself. If you had the set B, you could say B is a subset of B. You could say that the set containing 2, minus 1, and 7 is a subset of the set containing 2, minus 1, and 7, and on and on. But for a proper subset, that's not the case. It does not allow equality. It's the only difference between subset and proper subset. So for instance, whereas above I could say B is a subset of B, B is not a proper subset of B. And above where I said the set containing 2, minus 1, 7 is a subset of the set containing 2, minus 1, and 7, I have to say that the set containing 2, minus 1, and 7 is not a proper subset of the set containing 2, minus 1, and 7. Only that one single difference. Once you think about it, it should be easy enough. Do a couple of examples. Is the set containing A, E, I, O, U a subset of the set containing E, I, O, U, A? Remember, in sets, order doesn't matter. All you have to do is look. There is an A on the left that reappears on the right. There's an E on the left that reappears on the right. Same is true for the I, the O, and the U. So that is true. Yes, that is a true statement. How about this one? Is the set containing A, E, I, O, U a proper subset of the set containing E, I, O, U, A? Now remember, those are the same two sets. I just changed the symbol. So I know those two sets are equal from my previous work. But for a proper subset, you can't have equality, so that's automatically going to be no. The set on the left is not a proper subset of the set on the right because they're equal in a proper subset, and with proper subsets, that is not allowed. How about this? is capital N a subset of capital I? Remember, capital N is the symbol for natural numbers, so that's the set of counting numbers. Capital I is a set of integers. That includes the counting numbers, but it also includes 0 and the negatives of the counting numbers. So if you look on the left, everything on the left has a counterpart on the right. So yes, the set of natural numbers is a subset of the set of integers. Is the set of natural numbers a proper subset of the set of integers? Well, yes, because there's no equality. You can see that there are elements of integers that are not elements of the counting numbers or the natural numbers. So it is also true. Yes, the set of natural numbers is a proper subset of the set of integers. Let's list every subset of this set. Say we have a capital C set, which maybe C stands for condiments, and the elements are mustard, ketchup, onions, and relish. Starting off with the empty set, because we've already discussed that the empty set is a subset of every set. That's the only subset that doesn't have any elements. Now let's move up to the one element subsets. We'll just take each condiment one at a time and put it in a set. So you start off with mustard, you do ketchup, you do onions, you do relish. That's all the possible subsets with just one element. Now let's move to the two element subsets. Have to have some organized pattern here, so I'm going to start with mustard and match it with every other condiment. So I'll say mustard ketchup, then I'll say mustard onions, then I'll say mustard relish. I've matched mustard with every condiment. Now I'll move over and do the same with ketchup. I've already matched ketchup with mustard, so now I'll move to ketchup with onions and then ketchup with relish. Now I've matched ketchup with every condiment, so now I'll move to onions. Well, the only condiment I haven't matched onions with is relish, so I match onions with relish. Now let's move to the three element subset. The easiest way to think about this, there are only 4 elements in the whole set, so you'll get a 3-element subset by eliminating a condiment each time. So if I eliminate relish, I get mustard, ketchup, onions. If I eliminate onions, I get mustard, ketchup, relish. If I eliminate ketchup, I get mustard, onions, and relish. And if I eliminate mustard, I get ketchup, onions, and relish. And I claim that the only remaining subset is the 4-element subset consisting of the set itself. In other words, all of them. So how many subsets does that represent? If you count them, you'll find out that a 4-element set has 16 subsets. If I change it to proper subsets, remember the only difference is whether the set itself is a subset. So if I'm doing proper subsets, I have to leave out the set itself, so the 16 drops down to 15. So if I'm counting proper subsets, there are only 15. It's always true that the number of proper subsets is 1 less than the number of subsets. Let's see if we can find a pattern here. We know that a set with no elements has only one subset, namely the empty set, and that a set with one element has 2 subsets, namely itself and the empty set. And although we haven't done it, it's easy to show that a set with 2 elements has 4 subsets, and a set with 3 elements has 8 subsets. We just discovered that a set with 4 elements has 16 subsets. Let's see if we can devise a pattern. If you look at this following information in table form, you can see that if a set has no elements, it has 1 subset, 1 element has 2 subsets, 2 elements has 4 subsets, 3 elements has 8 subsets, 4 elements, 16 subsets. I'm looking for a pattern here. Do you see one? Do you see something that might be a possible pattern? Notice that each one of those number of subsets is a power of 2. 1 is 2 to the 0, 2 is 2 to the 1, 4 is 2 to the 2nd, 8 is 2 to the 3rd, and 16 is 2 to the 4th. It seems as if the number of subsets is 2 to the power of n, where n is the number of elements. Although we've not proven that that pattern continues, it turns out that it does. So we have the following result. A set with n elements has 2 to the power of n subsets. And because we already know that the number of proper subsets is 1 less than the number of subsets, we also have this result, which says that a set with n elements has 2 to the power of n minus 1 subsets, 1 less. Let's look at this example. Suppose a restaurant sells pizzas for which you can choose from 7 toppings. How many different variations of pizzas can the restaurant serve? Think about this. You could have a pizza made with no toppings. How yucky would that be? Or 1 topping, or 2 toppings, or 3 toppings, or 4 toppings, or 5 toppings, or you could say put all 7 toppings on there. Well, that just means we're looking at toppings as elements of a set, and we're looking at how many subsets of toppings can you have on your pizza. So there's an analogy there between subsets of a set and subsets of toppings to be put on the pizza. That means there are going to be 2 to the 7th, which is 128 variations of pizza from this restaurant if you count a no-topping pizza. So you could have a pizza with nothing on it. You could have pizzas with just 1 topping, pizzas with just 2 toppings, 3 toppings, and you can see that's just like counting subsets. So this idea of subsets can be very useful in counting problems. Relating this back to your calculator, you're going to be using the calculator a lot in this course, so you need to start learning how to use it. There's a button which I call the power key. It has an X with an exponent of Y, and that's your power button. So if you wanted to find out what 2 to the 7th was in the most efficient way, you would enter 2 into your calculator, press the X to the Y key, type in 7, and then press equal, and that would give you 128. How about this? What is the minimum number of toppings the restaurant must provide if it wishes to be able to advertise that it offers over 1,000 variations of its pizzas? Well, first of all, we know that 7 toppings is not enough because 7 toppings only produce 128 different variations of pizza. So that's not big enough. So my suggestion is you just start off knowing that 7 is not enough and keep going up until you pass 1,000. So if you do 2 to the 8th, you'll find out that's 256. That's not enough. If you do 2 to the 9th, you'll find out that's 512. That's not enough. But when you get to 2 to the 10th, you finally passed 1,000 variations of pizza. Restaurant would have to have at least 10 toppings before it can legitimately advertise that it can provide over 1,000 variations of its pizzas. We want to continue our discussion of Chapter 2 on sets by covering Section 2.3 on set operations. The intersection of 2 sets A and B, written as you see on the screen with the arch shape or upside down U shape between the sets A and B. That's the symbol for intersection. The intersection of 2 sets A and B is the set of elements common to both sets A and B. Using Venn diagrams, you can illustrate the intersection by looking at the overlapping areas of the circles that represent A and B. So the intersection is the overlapping part, the elements that are in common to both sets. The union of 2 sets A and B, written as you see on the screen, which is the arch turned upside down, sort of a U shape, A union B, is the set of elements that are members of either A or B or both. They can be members of A, they can be members of B, or they can be both, but they don't have to be both. That's the union of 2 sets. Looking at it with a Venn diagram, the union is everything in either A or B or both. For example, use the given sets. A is a set consisting of the numbers 1, 3, 5, and 7, and B is a set consisting of the numbers 3, 4, 5, and 6 to find A union B and A intersect B. We can do it with the Venn diagram just to see it more visually, but you don't have to have the Venn diagram to do these problems. I want to illustrate it with a Venn diagram just to show you the visual representation of it. A is a set containing the elements 1, 3, 5, and 7. B is the set containing the elements 3, 4, 5, and 6. And notice that 3 and 5 are in both sets, so I put them in the intersection of A and B in the overlapping area between the circles A and B. So if I want to find A union B, I'm looking at what's in A or B or both. So that just throws in anything that was in either one gets tossed in to the union. So the union of A and B is a set containing 1, 3, 4, 5, 6, and 7. Now the intersection are the elements that are in common to both sets, and if you look at it in a Venn diagram, that's in the overlapping area, what I sometimes call a football shape, that represents the intersection of A and B. So the intersection of A and B is a set containing 3 and 5. Two sets are disjoint if their intersection is the empty set. In other words, if there is no overlap, then there's nothing in common between the two sets, so the intersection is empty. And two sets are said to be disjoint if their intersection is the empty set. Looking at it on the Venn diagram, there is no overlap. And symbolically, you can say A intersects C is the empty set if the sets are disjoint. Take this example. If A is a set containing 1, 3, 5, and 7, and C is a set containing 2, 4, 6, and 8, find A intersects C. Well, again, if I choose to use the Venn diagram, A is a set containing 1, 3, 5, and 7. C is a set containing 2, 4, 6, and 8. Notice there are no elements in common between those two, so those two sets are disjoint, and the intersection is the empty set. In mathematical problems that involve sets, the word "and" typically means intersection. For instance, the phrase "the elements of A and B" means the elements of A intersect B. Similarly, the word "or" typically means union. The phrase "the elements of A or B" means the elements of A union B. For example, write a sentence that describes these sets. Notice the parentheses. You have to work with order of operations. The parentheses says to do the intersection first. So you're going to intersect B and C at some point. The union symbol means "or." The intersection symbol means "and." So we would read this: the set of all elements that are in A or are in B and C. Now, we're using the comma as a substitute for the parentheses. In the symbolic way of writing it, we'll use parentheses for grouping, but when we're saying it or writing it as an English sentence, we'll put a comma where the parentheses would begin. So in this sense, A is by itself on the left side of the comma. Everything on the right side of the comma is grouped together, which tells you when you're writing it symbolically to put the B and C in parentheses. So this is just something you'll get used to in this course, that the comma, when we're writing out an English sentence, takes the place of the parentheses when we're doing mathematical notation. So watch for the parenthesis in the mathematical writing of it and translate that into a comma. And when you see a comma in an English sentence, when you're going backwards and writing the symbolic version, you'll be using parentheses with everything on one side of the comma in parentheses, if there is more than one thing. On the left side, A is by itself, so you don't need parentheses. So you'll practice this throughout the semester and get used to using that comma as a grouping symbol. And again, just for emphasis, when you see the comma, you know if there's more than one thing on either the left or right of that comma, there are going to be parentheses involved when you go back and write it symbolically. Conversely, when you see the parentheses in the symbolic way of writing it, when you write it as a sentence, you're going to have a comma just before you start your parentheses. Might take a little getting used to, but it's not difficult. We're simply using that comma as a grouping symbol. How about this? J intersect K complement. So we're intersecting J with the things that are not in K. And is intersection. So you'd read this, the set of all elements that are in J and are not in K. So we're simply practicing saying and writing these mathematical statements in common English. Venn diagrams, as I've said before, are useful, and one thing you can use them for is to decide whether certain expressions involving sets are equal to each other. For instance, let's decide where this expression, the union of A, B, complement, in other words, the complement of the union of A and B, is the same as the intersection of the complement of A with the complement of B. And Venn diagrams are perfect for doing that. Let's start with the first one. It's the complement of the union of A and B. I would start off drawing the union of A and B because that's easy. It's just the area inside of either or both circles. The complement, though, is everything that's not inside the area represented by the union. So the complement of A union B is the area outside of both circles. Now move over to the other one and look at it. I want to do an equivalent picture of this. I'm intersecting the elements that are not in A with the elements that are not in B. So if you think about this, A complement, I'm using a horizontal series of lines to illustrate A complement. It's everything outside of A. B complement, I'm using vertical lines. Everything outside of B is B complement. Intersection means and it means overlap. So the intersection of those two sets are the areas that are cross-hatched both horizontally and vertically. And if you look closely, you can see that that area that I've sort of shaded in gray is the area that got cross-hatched. In other words, has horizontal and vertical lines. And if you look at those two things, you can get rid of all the lines I drew earlier and see that the shading on the left and the shading on the right are the same, which means those two statements are equal to each other. If the shading is any different at all, then the statements are not equal to each other. Unions and intersections can be done with more than two sets. We will see three sets done quite often. In the case of multiple set operations in one problem, always do the parentheses first and then move outward. So if you're considering the set A, which consists of the letters S, O, L, A, C, E, the set B consisting of the letters L, E, C, T, U, R, N, and the set C consisting of the letters M, L, S, E, R, Y, that's an L, not an I. Perhaps we want to find the union of A with the intersection of B and C. There's no necessarily single way to get started, but since A is sitting right there on the left, I might go ahead and just put in the set S, O, L, A, C, E for that. And then you might go over and look on the right side of the union symbol and you see that B intersects C. B intersects C means the elements that are in common to B and C. So if you look back up at B and C, you can see that they both have the L in it, they both have the E, and they both have the R, and that's it. So the intersection of B and C, you can sort of look back up and see that pretty easily. So you can see that the intersection of B and C is the set containing L, E, R. Now you're ready to take the union of that set with the set A, and that means you just take everything. If it's in A, you list it. If it's in B intersects C, you list it. If it's in both, you list it. So you just list every single letter you see down there on the bottom line. And if you look, there's an S, there's an O, there's an L, there's an A, there's a C, there's an E, and there's an R. So the union of A with the intersection of B and C consists of the set containing the letters SOLACER. You could do that with Venn diagrams, but as I said earlier, you can do these problems mostly without Venn diagrams, although Venn diagrams can be useful as a visual aid. How about this one? We want to find the intersection of the union in A and B with C. So this time you might say, well, okay, I start off with A union B. That means everything in A or B or both. So if it's in A or B or both, I just throw all the letters into one set. You don't list one letter twice, even if it appears twice, but you put every letter that appears in either set in the resulting set. So A union B, there's an S, there's an O, there's an L, there's an A, there's a C, there's an E in A. And then when you look over at B, you've already listed some of the letters, but you do have some extra letters that weren't listed earlier, in particular a T, a U, an R, and an N. So A union B is a set containing SOLACETURN. Now on the other side of the intersection symbol you have C, and because we're getting way down on the slide, I'll just relist what C is from up high. C is the set containing MLSERI. And now I'm doing intersection. Intersection means overlap, which means the elements are in common. If you look through there, both have an S, both have an L, both have an E, both have an R. So the intersection is the set containing S, L, E, and R. And there you go. This is not difficult, but you do need to be careful, and you need to pay attention to the grouping symbols. Venn diagrams can also be drawn to represent the relationships between three sets instead of just always two sets. Once you get beyond three sets, Venn diagrams are not very helpful. But for two or three sets, Venn diagrams are very useful. So if you have three sets, you have to write them this way so that you have the overlapping areas between each pair, plus you have an overlapping area for where all three circles intersect. So if I wanted to shade the intersection of A and B, I would have that, what I sometimes call a football-shaped area that represents the overlap between A and B. If I wanted to shade the intersection of A and C, I would have that, again, that football shape that represents the overlap between A and C. And if I wanted to shade B intersects C, I would take the overlapping region between the sets B and C, and that would be B intersects C. What about A intersect B intersect C? Those are the elements that are common to all three, and you can just see this without doing anything, that the overlapping area for all three sets is that sort of pie shape where all three circles intersect. So that's A intersect B intersect C. How about this? A intersect B complement. Intersect means overlap. So first of all, I might say, in my mind, just read it to myself or say it to myself, this represents the elements that are in A, but at the same time not in B. So it's inside of circle A, but outside of circle B. And if you just say it to yourself that way, you can picture the solution set without really doing any intermediate work. The elements that are in A, but at the same time, they're not in B. And the missing part is the part that would overlap into the circle B. I want to mention this just because I think it's important to know it exists. We're not doing much formally with all these properties of sets, but just like properties in algebra with commutativity and associativity and distributivity, we can do the same thing with sets. I just wanted to show you that those things exist. We really don't have much use for them in what we're doing, but they're important if you do more involved things with sets. Here's a really important application of Venn diagrams. It has to do with doing blood groups and blood types. Karl Landsteiner won a Nobel Prize in 1930 for discovering the 4 different human blood groups. He discovered that the blood of each individual contains exactly one of the following combinations of antigens. If you have only A antigens, you're called blood group A. Venn diagram wise, that would be shading the part of circle A that doesn't overlap into circle B. If you have only B antigens, you're said to be in blood group B, and you'd illustrate that on the Venn diagram by shading the circle B, but not bleeding over into circle A at all. Or you could have both A and B antigens. That would be blood group AB. And if you have A and B, that would be the intersection. That would be the football-shaped region where A and B intersect. Or you could have no A antigens and no B antigens, and that's called blood group O. And type O is the area outside of both of the circles. In other words, you're shading things that aren't in either circle. That's blood group O. So Venn diagrams are very useful for doing this. In 1941, Landsteiner and Alexander Wiener discovered that human blood may or may not have something called an Rh factor. Blood with this factor is called Rh positive, and you denote it by the letters Rh with a plus sign. Once the Rh factor was discovered, the Venn diagram goes from having 2 sets, A and B, to having 3 sets, A, B, and then a circle for the Rh positive factor for having the Rh factor. That's Rh positive. So we throw in an Rh plus circle. It makes it more complicated, but it does explain how the Rh factor fits in with the blood types. This diagram makes it clear that there are 8 different blood types. If you look at the Venn diagram, you can see where all of those lie, and we're going to go into more detail with that in a moment. The point is, this Venn diagram illustrates the 8 blood types considering the A antigens, the B antigens, and the Rh factor. It breaks it up into 8 blood types. Anything that's inside the Rh positive circle is going to have a plus. Anything that's not inside of the Rh circle will have a minus. So when you're assigning pluses and minuses, anything that has a presence inside of the Rh plus circle is going to have a plus. Everything else has a minus. Let's show how simple this really is. Let's take these 4 people, Roberto, Sue, Alex, and Lisa, and the arrow points at where they lie in terms of these 8 types. And let's see if we can classify them. Let's start off with remembering what everything means. Type O happens if you're not inside either A or B. Type AB happens if you're in the intersection of circles A and B. There's a plus if you're inside the Rh plus circle. There's a minus if you're outside the Rh plus circle. With that information, we should be able to classify all 4 of those people. So let's start off with Alex. Alex is inside of the A circle, and Alex is also inside the Rh positive circle. That means Alex is A positive. Lisa is not inside of either A or B, so Lisa must be an O. But Lisa is inside the Rh positive circle, so Lisa must be O positive. Sue is inside the A circle, but not in the overlap. But Sue is not in the Rh positive circle, so Sue is a negative. Sue would be A negative. And finally, Roberto is in the overlap between A and B, so Roberto is an AB, but Roberto is not inside the RH positive circle, so Roberto would be an AB negative. So you can see how easily this works once you remember those four things in the remember column. Let's look at one more example. Here we're asked which Venn diagram places each element below in the correct region. So we have the universal set consisting of the elements Sue, Bob, Al, Joe, Ann, Herb, Eric, Mike, and Sal. A consists of the set containing Sue and Herb. B, Sue, Eric, Joe, Ann, and RH positive, Eric, Sal, Al, and Herb. Now there's more than one way to approach this, but my suggestion is to start with the extremes. I would first look for the elements that appear in all three. And as you know, that's the dead center middle, and there aren't any. If you look, Sue is in A and B, but not a RH plus. Bob is not in any of them. Al is in RH positive, but not in B, or A for that matter. And you can go one by one, and you can see there are no elements, there are no people who are in all three. So that middle area, which represents the overlap of all three, should be empty. So that already knocks out the first and the last Venn diagram. Now the other extreme would be to look for the elements that appear in none of the three sets. In other words, is there someone or more than one person whose name doesn't appear in A, B, or RH plus? If you go through and look, Sue does, but you notice Bob is not in there. And if you go one by one, you get near the end when you find another, and that's Mike. Mike is also not in any of those sets. If you go one by one, the others are at least one of those sets. So Bob and Mike are the only two that don't appear in any of the three sets, and that knocks out the third choice and leaves you only with the second choice, which shows you with Bob and Mike outside of all three circles. So that tells you that the second choice must be the answer. Now, if you really wanted to be thorough, you could continue the verification process for elements belonging to just one set and just two sets. But because choice 2 is the only one remaining, unless you've made some silly mistake, that one has to be the answer.